Okay, so thank you, Vladas, and thank you for the invitation. I hope not too many of you are stuck in this morning's traffic jam still, so that people don't show up after I said important things in the introduction. We'll see. So, as you probably know, the goal of these lectures is to present some of the ideas and results and concepts that have emerged in the last years in order to understand better the two-dimensional critical systems and to understand these things from a mathematical perspective. And I mean, this is a very large subject, and 1 month wouldn't be enough to really cover everything. So the choice was basically to focus on some specific things that we believe are sort of the first thing to understand, and that also give a good idea of some other other concepts and ideas that then come later on. So sort of an entrance gate to this world. And the other thing, of course, you have noticed that it is recorded, and so usually when you are recorded, there are two options. You know, either you start being serious and you are inhibited, and I mean, you stop doing bad jokes and saying stupid things because you are afraid that it's going to be recorded and everybody can have a look at the stupid things you say. Or there's the other danger. You have the type of people who, you know, when they are unsecure, you know, when something is not exactly the way they believe it should be, then they make it even worse, and they start making even worse jokes. And okay, I will tend to be in that last category. So we'll see. So maybe I mean, since this is sort of I mean, there have been many or several lectures and classes on this topic. Maybe it's a good idea to have just to make a little backup and see basically where you are, what you know, what the global picture is, before moving on to. So basically today there will be two parts. So there will, before the little break, there will be basically the global picture and trying to see what we are after in this series of lectures. And then in the second one, I will really start describing this SLE process, which is one of the main goals of these classes, which is basically to, for those of you who don't know it or who don't know it well, to get some intuition and understand that it's a natural object, that it's not complicated. I mean, that basically the ideas come first and then the technique comes later, but the techniques, once you have the basic ideas, are natural things. And even though, I mean, for probabilists who are not sort of very confident with complex analysis, they might be afraid at first, but then you quickly realize first that if you are a probabilist, then you are in good shape in order to understand complex analysis because it's closely related anyway. And the second thing is that the complex analysis that one needs here is not really extremely complicated. So if you understand a little bit what harmonic measure is or extremal distance, and then you're in good shape. So we'll discuss these things. So if you remember, sort of basically there are three things that we would like to explain in this series of lectures in this course. And all three are related to phase transitions in two-dimensional statistical physics. And there are different ways basically to approach this. So the first one that you have been seeing so far is basically look at a sort of a discrete model. So you have seen percolation. Some of you probably know. the Ising model, or there are other models called the random cluster models that are related to the Ising model and their generalizations. And so basically these are models that live in 2 or 3 or any dimensions on a discrete lattice. And these turn out to exhibit phase transition. So, okay, you have seen already percolation. And so in the case of percolation, Vladas has described you the fact that if the parameter you play with, which is the probability that each site is open or closed, if this is small, then you don't have an infinite connected component. If P is large, you do have an infinite connected component, and that there's a critical value which separates these two phases, right? And so they exhibit phase transitions. So there exists phase transition. So of course, for each model, when we speak of a model, we just say the definition of the object and also what question we are looking at, right? When we say percolation, of course, we mean that first of all, you toss IID things. So at each cell, you just toss a coin independently of the others, and then you also say implicitly that what you are interested in is connectivity properties of the set of white cells or something like that in the picture, because I mean, tossing coins, you might look at other things. You know, is there a majority of white cells or black cells or other questions? So when we say percolation model or Ising model or things like that, usually we refer to first the model, which is the probability measure that we use to define it, and then also the type of questions we are interested in. So in the percolation picture, it's about connectivity properties. Okay, so there's a phase transition, and so there's a critical model, which is the model when the parameter is exactly at the value at which there is a phase transition. So, okay, I know you have followed Vladas courses, so I don't need to give too many examples, because you already all have a good example in mind, which is basically the critical percolation picture in the triangular lattice, which could be viewed as, you know, you have the hexagonal cells, you have a honeycomb lattice with white and black cells, and each cell is colored in white or black with probability 1/2, and you look at the large-scale connectivity properties of this, and this is a critical model. And what you are interested in is looking at the large-scale property of these critical models. Okay. And basically, probably you know, you have heard this already, but I just give another fresh little bit of painting on, refresh the painting on the wall, which is that basically what you have seen, for instance, in the subcritical case, so in the case where you are not at the critical value, Vladas has shown to you, for instance, that the probability that there's a large cluster from the origin up to size, I mean, up to distance n, decays exponentially with n, right? So you have done this Menshikov proof or something like that. So if you think about what this Menshikov or this Eisenman-Barsky result says, it says that if you take a box of size n, right? Okay, in a box of size n, you have approximately, say, n squared or n to the d sites, and each individual site has a probability, the probability that this site is in a cluster of the diameter larger than k will decay exponentially in k. Right? So that means that if you are in the subcritical case, if you take a box of size n, and you look at the largest cluster in this box, right? Then it's not very difficult to see that with high probability, the size of this large cluster, the largest cluster in this box, will be of order log n. So that just follows from the exponential decay property. So here you have a box of size n, and in all the clusters, you know, are of size smaller than log n. When I say cluster, the connected component of, say, black sites. If the probability to be black is smaller than 1/2 strictly. And so, in terms of connectivity properties, if you let n go to infinity, this log n, you know, if you rescale things and just look at the square as if it would be a square of size 1, with mesh size 1 over n, basically the clusters become smaller and smaller, and in the end, you see nothing. There are no connections anymore because all the clusters are of size much smaller than the square you're looking at. Okay? So that in some sense, what you see in the scaling limit, or on the large scale, it becomes deterministic. Right? There are no clusters once you rescale. And on the other side, of course, you might say the same. I mean, that the clusters of the other color basically are very small, and that then therefore you have one huge, you know, cluster that spans the entire square if p is strictly larger than 1/2. So again, that you have something deterministic. And of course, it always depends on what the question is that you're looking at. But roughly speaking, what you have is that in both cases, you have some sort of averaging procedure that tells you that the larger you become, basically, the closer to something deterministic you are, and so there are no real surprises in these phases if you are strictly below PC or strictly larger. Of course, there are many interesting questions, right, that you can ask if you look at off-critical, I mean, at models when P is not exactly equal to PC, but for, say, the large-scale connectivity properties, that's what happens. Now, what happens also is that when you are exactly at PC, and this is basically sort of trivial in the case of percolation, and in most other cases also, which is that probably you have seen this picture many times, that basically if you have a rhombus like this of size n, and if you look at the connectivity properties, if you are at p equal 1/2 on the triangular lattice, or at or if you fill in small exact hexagons, depending on how you look at your triangular lattice. Is that I mean, you should intervene if you think that what I say is too close to what you've already seen, or whether I should specify some things. So you should not be shied off by the fact that you will be recorded too if you ask stupid questions. I mean, a good course is a course when there are many stupid questions. So, because you should not, I mean, the goal is that you understand what is going on. So if you have a question that is blocking you, you should just raise your hand and ask it. Right, what I'm saying is that at p equal 1/2, the sort of seed that you are using, that on top of which basically everything has been proved in the courses, when you look at Russo-Seymour-Welsh, lemmers, and things like that, which are also one important seed to prove Smirnov's theorem, as you've seen yesterday, I think, or the day before. That basically the probability that there's a wide crossing, say from left to right of this rhombus, is exactly 1/2, regardless of the size of the rhombus, right? So because either you have a left to right crossing or you don't, and that means that you have a top to bottom crossing of the other color that is blocking you. And here, of course, you are using some very specific properties already of the triangular lattice. Okay, so here you already see that at the critical value you have some random events, right? The probability of crossing is 1/2, so that means that on large scale, you know, sometimes you have a crossing, sometimes you don't, and so that you see a random behavior on large scale when you are sitting exactly at this critical value. And this is supposed to be true for sort of many models in statistical physics, so this is not specific to the percolation case. so, for instance, for the Ising model or for these other models that you have there, you also have or expect, or you can prove in certain cases that when you're exactly at the critical value that you see some random behavior, because basically there's a even competition between the two phases, and if this competition is really even, then sometimes locally this one wins, sometimes locally the other phase wins, and on a larger scale they still compete on even grounds, and then on larger scale, at each scale, sort of one of them locally wins, but can lose on the higher scale. So you have this sort of idea of, scaling, or what physicists call, renormalization, group analysis, or this sort of things that also reminds some arguments of our colleagues who have been studying these off-critical cases, which is basically, you have a box like this. I mean, you look at what happens here, and you see something which is random, and then on a higher scale, say, if you look at what happens here, this one will be just one part of this, and then here you have something else that happens, maybe here, and so maybe on larger scale here, the other color wins and makes a crossing, and so on. So you have this idea that at any scale, because we know that at any scale there will be random behavior, that in certain way this propagation, of randomness from one scale to the other, from one scale to the other, will have something stationary with respect to the scales, and that we try to understand. Okay, so what happens is that so this is supposed to be true actually in any dimensions. So say in 3 dimensions, it's supposed to be true also that you have something interesting and random when you are exactly at the critical point. But it so happens that it's only when the dimension of the space is 2 that in certain cases you are able to control this randomness, large-scale randomness of these critical models on large scale. And the reason is that you have an additional tool in order to control these things, and this tool is basically conformal invariance or complex analysis, right? So conformal invariance or complex analysis, which is the thing that you can use in order to control these large-scale properties. So far, what you have seen in the case of percolation in 2 dimensions is Smirnov's result. And so Smirnov, for percolation in 2D, what you have seen is basically the following, that the probability, so that if you fix a domain D here and 4 points A, B, C, and D here, and you look at percolation on a fine mesh of size delta on some approximation of D here, that if you look at the probability here that there's a crossing in this picture from AB to DC here of a certain color, of a given color, what you have seen is that this converges as delta goes to 0 to some function f of D and the 4 points A, B, C, and D. And in fact, it turns out that, as you have seen in the proof, that this function is conformally invariant. And in fact, if you look at the proof of this convergence, if you remember how it works, you have first a little discrete combinatorial observation of flipping colors that is nice, and that if you think a little bit about it, that you can interpret as some sort of discrete analyticity or harmonicity property of a given discrete function. And then you manage, to control the fact that this discrete functions converge to the continuous one using precisely, discrete, almost analyticity property. And so in a way, the proof proves simultaneously, if you want, the fact that this converges. And the proof works also because the fact that what you get here, this function, you don't compute it explicitly, for each d, a, b, c, and d. You compute it, when you let one of the points d here vary, and when you and by showing that when you let this last point vary, then there is some analyticity behind the scene, and that there is some conformal invariance, and so on. So in Smirnov's proof, it proves simultaneously the convergence and the fact that this function f, is described by some analytic problem, which is conformally invariant in itself. So there is conformal invariance, and conformal invariance, which means basically that if phi is a conformal map, okay, we'll come back to conformal maps, from D onto some other D prime, that basically f of phi of D, and if you take the 4 boundary points, phi of A, phi of B, phi of C, phi of D, that this is equal to f of D, A, B, C, D. Right? So in other words, if you take one potato like this with 4 points here, and another, and say a rectangle like this, with the 4 points here, and if you know that you can map A, B, C, D, I mean these two on one to another by A prime, B prime, C prime, D prime, then the probability that you see a connection from here to here, when the mesh of the lattice goes to 0, converges to the limit of what you would see here when the mesh of the lattice goes to 0 here. Okay. So of course, and this I think Christophe has reminded you about Riemann's mapping theorem, and of course, basically what happens is that any domain, if I take a domain with 3 boundary points and another domain with 3 boundary points, there's always a way to map one onto the other in a certain way that to fix the 3 boundary points. That the image of A goes to A prime, the image of B goes to B prime, the image of C goes to C prime, and D is mapped onto D prime. So by an angle-preserving one-to-one map from D to D prime. So this is the basic Riemann's mapping theorem. And so therefore, it's not always the case that the last point D is going to be mapped onto D prime here. It's only, this only works, if the rectangle you have here is well chosen and the aspect ratio of the rectangle is exactly the right one, right? So, okay, we'll come back to that later. So I apologize if this is a bit quick or if I say things again that you've seen already. But what I want to emphasize here is that in this this theorem gives you one piece of information about the connectivity properties. It tells you if I take this quadrilateral, I know the asymptotics of this crossing probability. Now, maybe this is not exactly the question you're asking. Maybe what you are interested is something like, what is the probability that here in this quadrilateral, there is one cluster, such that that touches all 4 boundary segments, right? Or maybe you are interested in, and we'll come back to that later, maybe you are interested in actually what is the number of points inside the domain that are connected to the boundary. Right? That's a natural question to ask, in terms of applications or whatever. You imagine, say that, there is some infection or something tries to invade the domain from the boundary, and you raise the question basically how many points in the inside are going to be touched by this infection, if this infection only spreads on open sites or something like that. So, and if you think about it, this result is extremely strong and nice, but it gives you only the crossing probabilities for one given quadrilateral. And so even for this question, you don't know what the limiting, well, first of all, you don't know that the probability of this event converges to something when delta goes to 0. That's the first thing. And the second thing is you don't know it converges, and you don't have a guess about what it converges to. So of course you can try to use FKG inequality to say that, well, the probability to see a picture like this is, at least the probability that you have one crossing in one direction and one crossing in the other, but this inequality will not give you a precise answer because it's just a correlation inequality. It's not an inequality. It's not an equality. And in fact, in many cases, the natural questions that you are looking at, the natural object of interest is not sort of the first thing you can try to put your hands on by combinatorial methods. Okay. So, of course, when you teach or learn percolation for the first time, we say, okay, we are really interested in the crossing probability and the asymptotic value of the crossing probability. But of course, we cheat slightly because this is what we're able, to say something about. So we focus on, and the rest we just decide not to speak about it. But it's not necessarily the case that the crossing probability here in the rectangle is what you are interested in. So as you know, one of the thing that has sort of motivated mathematicians to look at this is, there were papers in the 80s by Cardy, Eisenman, and then Langlands and others who tried to say, okay, here we have an explicit formula given by Cardy for the asymptotic value of the crossing probability here. So this function here, f, that you've seen the other day with Vladas, it was a conjecture proposed by physicists using conformal field theory that this was the right function to look at. And so, of course, mathematicians were very, triggered. Were motivated to try to prove this because there was an explicit function. So if there's an explicit function, to derive, then, and if it's true, and obviously it was true because of simulation, there must be an explicit, a real mathematical proof to understand it, or some deep mathematical reasons for this to be true that were not really well understood at the time. Now, what Cardy, for instance, proposed, this method based on conformal field theory, they gave not only crossing probabilities, but they gave also values of certain critical exponents. So an example of a critical exponent that was produced by physicists long before mathematicians really could make sense or prove anything in this direction was, say, that example of critical exponent. And this is an example, and again, this is just one of them, and probably not the most important of them, physically speaking. Probably if you've been to Pierre's class or course yesterday, he has probably mentioned, the fact that there's one 4-arm exponent that plays a special role, and that in a sense is much more important than the one I'm going to describe now. But this one is at first looks like the most natural one, which is basically you take a big ball of size n, you take the center here, and you look at what is the probability that there is an open path, so a path made only of open cells that goes from 0 all the way to distance n. Okay. So because we know there's no infinite cluster, you know that this will go to 0, like when n goes to infinity, but you ask, at what speed, and the conjecture is that this probability decays like n to the minus 5/48 plus little o of 1 when n goes to infinity. So, and in a way, this type of result concerning critical exponents was what physicists were mostly interested in, because it had some, in many cases, a physical meaning, and could be used then to understand what happens not only when you are at the critical point, but also near the critical point. And I believe Pierre has discussed this issue yesterday. So if you think, okay, how can you, is there a way, you know, to prove this thing using directly Smirnov's theorem? The answer is no. You need some other input. This is not going to work, you know, to prove this type of result here. Okay, so that's basically the first thing about discrete. I mean, that you see in this course, which is the example of percolation, the fact that in certain cases, for certain discrete models, you can cook up a trick or identify inside the discrete model property that plays the role of approximate analyticity or harmonicity property, and that enables you to control what happens even on large scale and to prove that certain functions, certain probability converge when the mesh of the lattice go to 0, and that you can control things like that. So the second thing is basically motivated by this type of question, which is basically, is there a way to describe the limits, I mean the global picture of what you see in the limit, which is richer than just crossing probabilities? And so the second thing is basically understand the possible scaling limits of two-dimensional interfaces that are conformal invariant. So here, in this convoluted phrase, what I want to say is that what we're going to do is to say that instead of looking just at one number, which is a crossing probability, we are trying to look at something more, which contains more information. And one natural thing to try to do is the following. So I'm going to drive a discrete, first I draw to you the discrete picture, and then we will forget about the discrete, because the second item here will be just about, you know, continuous structures, and we will forget about the discrete case. And of course the third item, you know, the first item is prove that in certain cases you can control certain discrete observables when the mesh of the lattice go to 0. Second item will be understand, you know, some families of random curves that satisfy certain properties when defined directly in the continuum. And the third item will be, okay, how do you connect these two things? How do you prove that in a certain way what you understand in the discrete case is enough to prove convergence of the discrete interfaces to these continuous interfaces, and how do you use this to come back to the discrete models that you started with? So in some sense, how do you prove this, for instance? So let us for a moment still think about the discrete model. So remember, in the percolation picture, and actually in the other models too, if you think about it, one way to interpret them is that you have some sort of random coloring of the plane with two colors. And because you are you are coloring hexagons or small hexagonal faces or sides of a triangular lattice, and because of the specific properties of the lattice, what happens is that if you have a white cluster, so if you have a white island, you know, created by many white cells, then the outer boundary of this white cluster, you know, consists of a family of cells of the other color, of course, because they are, you know, that's what prevents the cluster to be larger, and then all these cells of the other color will be connected to each other. Right, so that basically the outer boundary of a white cluster is created by a color of the other color. By a cluster of the other color. So this is the similar, you know, type of exactly the same type of argument that tells you, you know, that the crossing probability is 1/2, because here, if you don't, you know, if there's no crossing, that means that if you look at the cluster of all white cells attached to the left part, that the outer boundary of this guy creates a top to bottom crossing of the other color. So, and this is just, about the fact that if in a triangle, you only have three corners. So if there's if this one is white and the other two are green, then the two green ones are neighbors. That's basically all there is there. So this means that it's really sort of a coloring of the planes where, the green and white ones, try to create territories and eat up territories and compete about basically creating large territories. So now if you have a domain D here, and now maybe it's the first time where now we take, with boundaries, we take only two specific boundary points, not four. One boundary point here, A, and one boundary point B here. And we take a very small lattice mesh, delta, of size delta. Now, what you can look at is the cluster, the green cluster, that is attached to the green part, the boundary of the domain that we have colored in green here. Right? If you look at just the union of all the clusters here that are colored in green here, you will, and that are attached to the lower part of the boundary, you see something like this. And you can go around basically the outer boundary of this cluster here. I guess this picture you have seen before. Right? And how is this, red outer boundary defined? It's defined by basically saying, on the right of this red curve, you have green hexagons that are all attached to this boundary. And on the left, because that means the cluster stops, so you have only white hexagons here. Okay? So what you do here is basically that you are coloring this, this domain in two colors, white and green, and basically you look at how deep does the white thing go that is attached from the white part, and how high does the green thing go when attached to the green part, and it just happens that there's one single curve, that separates, the bottom part from the white cluster, from the top part from the green cluster. So one way to understand this thing in the discrete case so I don't know, did you focus a lot on this exploration process idea in the discrete case or not so far? If you think about Stas's proof of conformal invariance, one way to view these things is to say, well, okay, everything starts with a discrete combinatorial lemma which has to do with changing colors. 3 arms in that configuration has the same probability that 3 arms in another configuration, and that this property basically is not a trivial thing, because one has to be careful, about are you allowed to change the colors in where you haven't explored things so far. So there's one delicate point where one has to be very careful not to claim something that is wrong about the fact that you first discover some cells, some colors, and then in the unexplored things you decide, well, now I could choose, flip all the colors in the cells that I have not discovered so far. And so again here you have exactly, and actually in Menchikov's proof and all these things, it's always about, you have these IID things around, coin tossings, and you have this mess, and you want to have a way to explore these things progressively. You discover certain things and you stop, and then you continue discovering and you stop, and by doing this, exactly, I have discovered the colors of these and that cells, but the things that I've not explored yet, they are ID and conditioning of what I have explored yet. Even if the shape of what I have explored is random, the remaining colors will be IID in the remaining domain. So a little bit like, when you study martingales or Markov processes, basically everything is contained in the Markov property and the notion of stopping time, and the fact that, you know, one, I have a stopping time given the fact information I've collected so far, I can say certain things about the law of the future. It's a little bit the same. You start discovering hexagons, colors, and then you know that conditionally of what you have discovered so far, the law of the rest is still IID in where I haven't discovered the color yet. And so the rigorous justification of this color switching is also based on the fact that there's a way, you know, to explore the arms in this free-arm event by exploration wise. So here, basically, what happens is that this red interface, did I change? No, it's okay. You know, it can be explored, you know, progressively starting from A. The idea is just, you know, you start from A. So here everything is white. Here everything is green. And now, because of this fact that, you know, you're on the triangular lattice, basically, you know that you have a white neighbor. You have here there's a white guy. There's a green guy here. There's a white guy there. So you look at the triangle here, and you say, is the next one green or is the next one white? Okay? Because you know that if it's white here, it will be connected to the white thing, and it will be in the white cluster. And if it would be green, it would be connected to this part of the boundary, and it would be in the green cluster. So in other words, here locally, you have one white one, one green one here, and here you have some blue one that you have not explored yet, and you don't know the color yet. Okay, and otherwise, basically, if you think about this in the triangular lattice, here everything here is white, here everything on the boundary here is red, is green. So here, the first thing you say, well, is this white or is this green? So what you do is you toss a coin to decide whether this one is white or green. So if this one is green, say, now that means that the interface that started here like this will have to turn like this. Okay, because it has to pass above this green one, because this one is on the green, is part of the green cluster here. And now you are raising the same question again, right? Because now you have a new domain which is created by this here. You have a new white boundary here, and now you enter in this domain through this edge, and you ask. Now the question is this guy here which maybe we can draw in blue? Is it red? Is it green or is it white? So you toss a coin and you see it's white, so you have to turn right. Okay. And you continue like this, right? And you make your way in between the white and the green cluster. And you can make it sort of progressively, you know, by exploring locally, you know, where does the red guy have to go? And what you see that in the end, eventually you have to end up here. And what you will have discovered in this picture is that all the neighbors on this side will be green, all the neighbors on this side here will be white, and you will not have explored anything else. Right? So a little bit like the three-arm thing, basically, so you explore this, and you know that the probability, you know that this discrete curve, exploration curve is equal, this red curve is equal to that, precisely that sample, you know, the probability to see this picture here for this green curve. This will be just 1/2 to the power number of discovered discovered colors in this process. Because you know that this red curve is this red curve if and only if all the boundaries, I mean all the things on the right-hand boundary that you have discovered are green, and the ones on the left-hand boundary are white, and this probability is exactly equal to 1/2 to the power's number of discovered neighbors. Okay. So what you see here in this picture is that it is very natural, you know, to try to discover, you know, the states, the colors of the different sites in this exploration process-wise, right? By just saying it, you have a natural way, you know, to discover progressively the colors of the percolation picture by, starting from the boundary. And you have a little local algorithm that tells you, how to continue. This algorithm is local, but it enables you to discover this global interface. And interfaces, of course, like this are intimately, are connected. This picture here is connected in some way to Smirnov's proof, because if you think about what you compute in Smirnov's or in Cardy's formula, imagine here that you have a picture here. You have D here, you have A here, and you have B here. Okay? Or let's do it the other way around, like so. A, B, C, D. Okay? And imagine that we play this game exactly as we did before by coloring here everything here in white and here everything in green. Okay. Now, is there a way to express the crossing probability that you have here in terms of this red interface, that goes from A to B? The answer is yes, because suppose there is a white crossing from here all the way to the boundary here. That means exactly that this red curve, this red interface, it will have to go around this white crossing, and therefore it will touch this interval CD. Right? So the probability that this discrete exploration thing, this red curve, touches this part of the boundary before hitting B is exactly the crossing probability, because if it does go all the way here, that means that here there is a cluster that goes all the way, because you are going around the union of all the clusters that touch the white part of the boundary. And conversely, if there is a cluster, then you have to go around it and you touch CD, right? So you see that in this particular example, the thing this crossing probability here can be expressed in terms of an exploration process like this. What happens is that in a similar way, and this is more complicated maybe here, maybe I will show you another example in a moment, but basically all the questions that you can try to study, in percolation, or almost all of them, can be expressed in terms of a certain event involving exploration processes. So maybe I give you just one example just to illustrate this, which is a simple example involving two arms. So imagine that you have the picture like this, and you have a point Z here in the middle. And you look at the probability here, say that there exists a green path originating from Z touching the green part of the boundary, and the probability that there's a white path originates from the white part of the boundary all the way to Z. Right? So that Z is sort of locally started from Z. You have two arms of opposite colors that join these two things. Well, if this is the case, then the exploration process here will have to go exactly through this point Z, because it will have to separate this green cluster from the white cluster. So what you see here is that the two-arm event here will play the role, basically. One way to express it will be with the probability that the given point will be visited by this exploration process. And so you start seeing that probably the number of points, on that, if we can understand the probability that the discrete exploration process goes through a given point, then you can start understanding things involving fractal dimensions or things like that. Okay, we'll come back to that later. So this was just a motivation to say that it is a natural thing to try to say, let's look, try to understand continuous, or possibly what could be the scaling limit when delta goes to 0 of the law of this red curve here. Because if you understand this, maybe this will be a good way to try and understand more and reach all these other questions. So what is a sort of so the idea is the following. So motivated by this, one tries to define laws of random curves in domains D with two boundary points here that satisfy certain properties. So what we want is that for any D AB, right, for any domain, simply connected domain D here with boundary points A and B, we roughly want one probability measure, right, which is the law of the interface, of what the interface, or the scaling limit of the interface would be if we take the mesh of the lattice go to 0 in this given domain here. So the law of this red, scaling limit of this red interface from A to B here. Okay? So what we want is for each domain D and each two choice of boundary points, we want PDAB, a probability measure on curves from A to B in D. Okay? So that's what we're trying to define. And here, you know, to make use of conformal invariance in the best way, it's convenient, you know, to look at what happens in different domains and try to compare what happens in this domain and this other domain and try to make use of this later, as you will see. So we try to define for each simply connected domain a random curve gamma that we want to think of as the possible scaling limit of the picture we have here. Now, we want this curve to have, I mean, these measures to have certain properties. So we want conformal invariance. So which means that for any phi conformal map from D onto D prime, we want that the image of the probability measure in the domain D with boundary points A, B is just the probability measure in D prime, A prime, B prime. So here you see we assume something much stronger than what we know, right? Because what we expect, you know, from Smirnov's theorem is that the crossing probability is conformally invariant. Which means that if there is a scaling limit, you know, if there is a red curve here, which is the scaling limit of the percolation interface, we know that, you know, if I fix two other boundary points here, the probability that it touches here is something which has conformal invariance in it, so that you can map on some other domain in there. Here we ask for something more, which is basically that if I have this red curve from A to B here, and the thing from A to A prime here to B prime in some other domain D prime, that these things are basically conformally equivalent, so that if there's a conformal map phi from this domain onto that domain, if I take the image of this random curve mapped onto the other domain, when of course the starting and endpoint have to be matched, then what I observe here has the law of what I would have observed directly here. Right? So here you see we start asking for something more than what you know so far, which is basically not only that the crossing probabilities are conformally invariant, but basically that the entire picture, that what you see here, you know, and what you see in some other domain, simply connected domain, these two things are, so they are random, whatever you look at, and they are conformally equivalent. That means that if you observe something here, and you map it conformally up to there, then you would observe the same thing with the same probability over there. Yes?
This red curve, exploration curve, tells you things about the interface between the green part and the white part.
Yes?
But it could be that there's more information in the...
Yes.
If there's a way to in some sense, rescale the process and maintain all the information of
Yes, okay, so that's a good question. What I will try to explain towards the end is indeed that once you understand the scaling limit of one curve, then you can try to also understand what you have not explored yet. But okay, this is more complicated. So now we just, in a way, what I want to explain, in the course is basically that once you have understood the scaling limit of these curves, basically you have access to everything that you have access to. There's no things that there are things you don't have access to, but these things we don't know if they are, there are no conjectures or anything about them. So, okay, so here we forget, in a way, we forget about the discrete structure, and we just say, we imagine, that the entire image of percolation that you see here in a fine scale and in another domain on the fine scale, that the entire picture is conformally invariant, and in a way, this is natural to assume this if you believe that, once you have the crossing probabilities, that it would be odd, that the crossing probabilities are conformally invariant, but some other properties, natural properties, are not. And I will explain you, that indeed, okay, we'll come back to that later. So we want this first property, and we want a second property, which is exploration. We want the law of these red curves to be, to have inherited from the discrete exploration things, the discrete some exploration. And so the idea is what you want is that these red curves, you want them, so you fix for any d, a, b. So we fix the 2 points A and B here. And we know the curve gamma. We know the beginning of the curve gamma. We know gamma here up to here. So imagine that we parameterize it by a certain time t. We know it here. So this would be gamma of 0. And imagine that you parameterize it in such a way that the curve here, the time goes to infinity when it reaches B. So behind the scene here already, you use the fact that there's a natural way to parameterize time that is intrinsic to the curve itself. That when you have reached here, you know at what time you've reached it in a certain way. You don't need to know what happens there to know how to parameterize time. But you don't need really to speak about time parameterization to state this exploration property, but still, it's a natural thing to do. So basically, what we want, and since this is a vague statement, I can be vague here also. What we want is that conditionally on gamma up to time t, right? So we have observed the beginning of this red curve. Remember, in the discrete case, what we had was that this discrete thing could be explored locally, just by seeing what, and so basically what, in the discrete case, what it means to have explored the beginning of the curve. So imagine that we know that the beginning of the curve goes all the way here. So knowing this discrete curves all the way up to here is exactly saying that the left neighbors are white, the right neighbors are green, and nothing else. And in the remaining thing here, you haven't conditioned on anything. Right? So in the discrete case, conditioning on the red curve here to go all the way up to here is exactly just conditioning on the fact that here things are green, here things are white, and here you haven't yet explored at all the state of the cells there. So which means that if you know that you are here, and if delta, the mesh of the lattice, is very small, what is the law of the remaining thing that remains to be explored? Well, you would expect it to be, so conditionally on gamma up to time t, the law of what remains to be explored here, so the thing in dots, is just the probability measure p. Now, with a new domain, because here, remember, you would like to say that here this is gamma of t. So what remains to be explored is a curve that goes from gamma of t all the way to b here, which is the boundary of that separates the white cluster attached to this part of the boundary from the green one here. Right? Because the past that you have discovered now is part of the boundary of your new domain, and you have explored exactly, so the color is exactly in such a way that what you have here is green on the boundary of this domain, and what you have here is white. So what you would expect is that this conditional law is the law in the remaining domain to be explored that goes from gamma of t all the way to b. So in a certain way here, what you have here is conditionally on this red thing, the law of the, okay, of the yellow one here is exactly the random curve that you obtain in the domain that you would get from here to here, right? With the boundary point here and there in this green domain. So basically, you want one, conformal invariance, and two, that these red curves that you define in the continuum inherit in a certain way this exploration property. So what I will explain after the break is that this plus this, in fact, already tells you, that there are not many curves like this. And it tells you two things. It tells you, first of all, that there are not that many random curves satisfying these properties. And second, that it tells you also how to define them. And this is Schramm's idea of defining the SLEs. And we'll see that after the break. So that is, in some sense, the second part, of this lecture series, which is saying, work directly in the continuous and try to define, construct or understand what these possible conformally invariant scaling limits are. And then there's the third part, of course, which is plug together the first two parts. So plug together basically sort of Smirnov's proof about crossing probabilities, and sort of these random curves and their properties, and show first of all one, which is that indeed the discrete exploration process converges to one of these Schramm-Loewner evolutions, right? So I just want to, to make to show you now sort of clearly how the things are structured. So what you start is the crossing probabilities. Then you have some idea, you have some intuition about what you should be getting as limits here of these objects here. And this is going to help you also to actually show just using Smirnov's proof. Right? Just using Smirnov's result. You don't need to know that everything is conformal invariant at that point. Just using Smirnov's result and Russo-Seymour-Welsh type arguments that indeed the discrete exploration process converges to SLE. And then once you have this, you can use SLE properties to derive properties, so further properties of discrete percolation. So, which is basically, for instance, the critical exponent. Or, as you said before, the fact that, in fact, everything is conformal invariant, even what you have not explored by the exploration process. And, of course, this is going to be probably, you feel that here that one has to do some technical things. You have to, if you want to prove convergence, a family of probability measures on curves, you have to do something. As you know from, say, standard invariance principles, or when you want to prove that simple random walk converges to Brownian motion, you have to be careful about what topology do you talk about, what you have tightness issues, you have to do things like that. And then you have to prove, say here, then you want to prove that certain probabilities, discrete probabilities, converge to some probabilities that have to do with SLE. So you have to prove in a certain way that in a way you have convergence of some functions of the discrete exploration process converge to the same functions of the continuous exploration process. So you have to prove that the measure on the continuous guys is supported on a set of curves on which these functions are continuous in order to have the prove that the discrete probability converges to the continuous ones and things like that. So there are things to be done there, but the nice thing about this entire theory is that once when you know that what you are aiming at, which is this SLE process, and you have Smirnov's result, then in some way things plug together fairly nicely, and it's not that bad. I mean, you have to, well, you will see. So I hope towards the end of the series here that you will basically have a global picture of how to prove, say, the 5/48 statement about critical percolation. But you have to go through this entire procedure to make it work. Okay, so I know there's an issue about recording minutes, so that we are going to have a small break. And so basically after the break, it will be sort of something quite different, because it will be just, speaking about this issue here. So what do you define? How do you define these random curves that satisfy these two properties, and how are you able to put your hands on it, and why is it natural to define it in the way it is defined once you have these constraints over here? So one important thing, and I don't know if I will have time, maybe we'll do some couple of afternoon sessions for those who are really interested in seeing this. There are not many models, discrete models, for which this picture here, like the one I described, the fact that you can control some discrete observables, show that they are conformally invariant in the scaling limit, show that the discrete exploration or interfaces converge to the continuous one, and then use this to come back to the discrete model in order to prove results about the discrete model. There are not many of them, because in a way you have to have some luck about the discrete model in order to have a discrete combinatorial observation, right? Okay, there is an indication that tells you that some discrete models are nicer or more suitable to combinatorial tricks than others. And for instance, because just as an example, you know that you have a good guess for what the critical value of the parameter is for the model to be critical. So in percolation on the triangular lattice, or this coloring of hexagons, we knew, we could guess from early on that the critical probability was 1/2. Okay. And so, this entire flipping, change of color stories and so on, it works only because you are lucky to be enough to be at p equal 1/2. If you would have done, say, critical percolation on the square lattice, on site percolation on the square lattice, there is no guess or conjecture about what the exact, analytic expression of the exact value of the critical percolation probability. It's 0.58 something or 57. You have to be careful because it's recorded. But it's, it's some number, but there's no explicit guess about what this number actually is. So you already see that there, in order to reproduce a proof like Smirnov's result, about convergence of critical, of crossing probabilities or something like that, you will have a very hard time, because you already don't know you don't have any way, to describe directly the model you are talking about. You just know it is the model where you have a phase transition, but you don't actually know what the value of PC exactly is. So you are in bad shape to prove, anything directly on the model. And you see that you will have it will probably require a hard time do something rigorously there. Maybe it will work at some point, but you have some additional idea. However, there are some exceptional models in statistical physics. So, for instance, Ising model in Z squared, or Potts models in Z squared, where you know, or you guess, using some type of symmetry argument, what the critical value is. And probably there is a way to make sense of a combinatorial trick. And this is what sort of Smirnov has been doing for the Ising model in Z squared. So basically, this picture I'm sketching here is true also for other models. So for Ising model in Z squared, it works. It's not written up completely. You know, Stas has the first preprint is out, the corresponding one to crossing probability convergence, except for the Ising model. But he promised to have the other ones out soon. And I know I know some preprints are circulating, and it works. But so just to emphasize that in the proof, I mean, percolation is a very special model because it has this independence property, right? It has this fact that, you know, to color the boundary in red or in white does not affect anything about what happens inside the domain. And at various places, you know, you have the impression that you're using something very special about percolation, which is this independence property of what happens at different places in the plane. And the fact that it does not feel the boundary of the domain in a way other models do. But I just want to insist that it's not true that this is crucial, right? Because for other models where there is a nearest neighbor interaction and things like that, you can do the same thing. So the specific property of percolation is not, you know, the essential thing that makes the proof work. It's more about, you know, the fact that there is a combinatorial trick to start with. And okay, we will probably come back to that later. So maybe we will, if you are interested, some of you are interested or express interest, we can try to do some sessions about the convergence. I mean, how do you prove things about the Ising model and so on. Of course, I have to make choices in the global lectures because, you know, I don't want now to spend 2 lectures introducing random clusters and models and doing things like that. I wouldn't have enough time then to, you know, explain you what SLE is and so on. So we make a break now, I don't know, 15 minutes or something like that, and then we continue with the definition or ideas that lead to the definition of SLE.